Okay, good morning, guys. So today we are gonna talk about the backward pass or backprop algorithm. So last session we mentioned about the algorithm that was proposed by Hinton and his collaborators in 1986 to downsize, to speed up actually the way the algorithm uh, does the backprop pass. Um, in your tutorial, you're going to see how you can apply it from scratch. You might not be able to get the O order of the same order as the paper, but definitely it's doable. So as we talked about it also before, this has to speed up uh, the applications of neural network in many domains because of its reasonable order. So you already know that for any sample neural network with sufficient hidden layers, so you're going to pass through the inputs, or if you are in the hidden layers in the middle, so we're going to call it xi l of l minus 1, so the l minus 1 layer. So each of those neurons are connected to the next node, and they're going to pass a signal, or what we call it sj, and you have to multiply these two to the weight, and then you're going to sum them up. This is a signal that goes into the nonlinearity, so it could be sigmoid, it could be hyperbolic tangent in this case, or the very first MLP that we talked about, it was perceptron. And finally, after your layer, so here, suppose that was your last layer, your hypothesis got something, and you have to compare it with your y, and then it's going to give you a loss function, and this is related to your weight, right? These are the model parameters. So using that, you have to devise a way to backprop all this error that you found based on each of the layers you had. So it's sort of a recursive function. So the outer one would be here. By outer, I mean the one closer to softmax, which is the last layer. And then the more you go inside, they are inner layers, like L layer, layers like these guys. And inside that, you're gonna apply it again. So if you take a look at the network from this location, you're gonna see these are the inner layers, right? But if you step one layer past, come here, this would be your outer layer, and this would be your inner layer. So and this gonna go recursively for all your network. So no matter how many hidden layers are. And so today we're gonna discuss about this. So if you want to formalize this, you're gonna have an input, a vector of x, and y would be the output, and we have loss function ex of omega, which I mentioned here. So this is ex of omega, and omega was our model weight parameters. One thing you can intuitively take into account is your hypothesis x, or the one you predicted, you estimated. Sometimes we call it hat here, and your y. So the error, the in-sample error out of this is completely related to your w's, because this is a constant, this is a class of the true output, right? And also x is constant as well, so h is directly correlated with w. That's why in order to calculate the backward pass, we have to update the weights here. Okay. Is it clear right now? Let me just clean this. So what we need to compute is the dE of x of omega divided by the wi and j of L. So these are the W's. It's like we are taking into account the how much weight should I change so that this E that I have is going to be proportionate to that. So you have certain E here. This will give you how much of changes here in W's you have to do. And this will be done step by step after gradient descent, and you're going to convert to your minimum, local minimum. All right. So this is another way to represent it. We talked about it mostly last session. I'm just going to bring them back up as a recap. So here, after you hit your final layer, that was your estimated value. So you're going to compare it with the y of x. So this g was the candidate one that you use from your hypothesis set, if you recall. And then we have to, and this is the a of x that we need to backprop and adjust the weight based on. Okay, so let's talk about chain rule. So you recall before when we talked about it. So basically, because we are dealing with so many layers, nested layers. So in calculus there was a simple rule called chain rule. So it basically says that if you want to compute a derivative of a function, and a function is inside that function, so you have to do it like this. So that the derivative of the outer function, you have to multiply it by a derivative of inner function. So say you have 2x plus 1 raised to the 6, right? So this is your y. So here would be your inner. I'm not sure how many n we had. Was it 2 for inner? And so this is the outer, okay? So if you want to divide y prime, so it's going to be 6 because it's going to come back forward. And here you don't touch it anymore. So you say 2x plus 1, and then you divide it to the derivative of the inside, which is 2, right? So the output would be 12. Sometimes we can do this recursively, and that's the case in neural network. Suppose you were dealing with maybe a cosine function or a sine function. Let's maybe we can say 2x to the raise of 2, right? So when you get the derivative, this will become minus sine. So you have 2 of 1 plus sine 2x, and then this becomes, the inner one becomes minus sine of 2x. But again, you have 2x here as the inner one, and then you have to apply chain rule one other time, right? So it's going to be recursive. Sometimes we have this thing. So this is basically what's happening here. Let me just. So your model parameters represent one EX, which was the error you found, and it's dependent on S, your signals, S1 up to SDLL, and your weights, right? So you're going to have two different functions here. But only Sj depends on Wij. So coming from, if you take a look at the neural network from above, so that's the last layer. That was your Sj. So all those weights connected to that. So if you have an error here and you want to estimate and you want to calculate how much of difference you have to change here, then you have to take a look at here and see what are the connected weights to that. That's why Sj is dependent on Wij's. And then you come back here, for each of them, you have to find the same thing again, right? Going from the last layer towards the other layers. So, and last session also we talked about this, how we're going to compute that. Sometimes we call this the partial as well. So partial. So partial x omega divided by partial Wij of L. So now this is exactly the expansion of the chain rule here. So up to this point, this is easy for us, right? Because we know when we are here, the last layer, when we estimate the in-sample error, we know how much of change we have to apply at Sj, right? Because that's the first thing that connects to that. But again, coming here, we don't exactly know how many weights were behind this. So this should be expanded again and again and again, up to the first layer. And then, so recall, this value, as I mentioned there, because of all those weights, incoming weights, you have to make a summation, say R from 0 to B L minus 1, all those x's and weights that are in the previous layers. Plus, if you make the derivative of both those two, you're going to have xi L minus 1. So now we pass from this layer, we computed the partial changes that needs to be done here, and then we go back up one layer to the L minus 1, right? So this is the value for this. And we have to go forward with that, right? Okay, so now we arrive at a point that we know in high level what's going to be the partial Sj of L divided by partial Wij's. And we found that if you want to change this, you have to go inside that, and for all of those xi's of the previous layer, and we defined a delta j of L equal to the first value of our chain rule. So let this be partial EX omega divided by SJL. Now that previous formula becomes this, right? We computed that, and this is the delta J. Okay. And going forward, if you want to make a partial out of that, so we're going to see that if you define them in vector space, so you're going to have deltas, the vector of delta L from delta 1 up to delta D, L of L, and you have xi's in the previous layer, which they contain x0, L1 up to xd L1, L minus 1 of L minus 1, right? And we reach up to the point that we say, okay, in order to compute the partial of En of our weights, with respect to those weights, so we need to compute the xi of the previous layer, or layers, multiply by something, we call it delta L. And this is a transpose of the vector in vector space. So how are we going to compute that? So we have to carry on expanding the chain rule for the previous layers as well. So in order to do that, we're gonna discuss about two cases. One simplified case at the very last layer, and then the second case when we are in intermediate layers. How are we going to compute this in these two occasions? And then we can generalize based on these two cases. Questions? Yeah. All right. So the first case, the simplified case that we only have the last layer and we want to compute the delta for what is previous layer. So it's as if we have so I'll hold for another minute. Okay, so for simplicity, consider your L as capital L, so we are only targeting the last layer. And let dl, the capital L, is equal to 1, just again for simplicity, is as if we have crisscrossed this S of L, so we only have this, and so suppose that was only a case for linear regression, right? So we were using mean square error to find the in-sample error, right? So in that case, we would have something like this. So that was our the G function, the candidate one, from our hypothesis that we chose, and based on that we estimated an error, so E of n of omega. So in this case it could be anything like mean square error or other things, right? So what would be the delta in this case? So delta capital L would be the partial En omega divided by partial SL, because we are only here, so we are here, and right? We want to make sure so we have an error here, so we want to see how this error was affected by changing the previous value, and the previous value was coming from this, right? So you can expand using the chain rule. So it's going to be equal to partial En omega divided by partial x capital L multiplied by the inner function, which was the partial xl divided by partial SL, right? So divided by this to that. And then suppose this nonlinearity was theta or sigmoid function or hyperbolic tangent or anything. So we found that XL, the capital L, is equal to the output of that activation function of S1, right? Because this one, the output of this would be this, right? Thus, if you make a partial out of this coming inside, so that would be this. The partial of this itself would be the theta prime multiply S1. So if you recall, when I was talking about sigmoid and hyperbolic tangent, I was mentioning some of these properties. So one of its good properties is when you make a prime out of that, you still have the same function, so the calculation would be easier, right? Because it was sigmoid or hyperbolic tangent, normally is the prime of that would be 1 minus theta to the raise of 2. So this came from here, this came from there as the output of that calculation. So in a simplified case that we were only targeting the last layer without many S's before, so the delta L can be computed as theta prime SL, and then your the output of your partial derivative of your error function, right? In this case, it was mean square error. If you wanted to mention it, expand it more, so this would be, this itself is 1 minus theta to right of S. This is the value of theta prime. Now, let's talk about another case which is more complex. So suppose one intermediate level, so when you are inside your neural network, surrounded by some layers left and right, so how are we going to compute delta in that case? If you manage to find that as well, combining this with that, we can generalize the whole back problem. Okay. So now we're going to compute the delta I of L for an intermediate node. Here, suppose you are in them at this location. So you have one delta L plus 1 coming from the succeeding layer. So now you want to compute that towards the rest of your network, right? So here you have to take into account that this one was connected by many neurons before. So this is only one node, right? So the other nodes would have connections there as well. That's why I represent it here. So suppose you had like 3 nodes here, 4 nodes in the previous layers. So this one, that theta itself, was connected with all those 4 layers behind, right? So if you want to calculate the delta here, it is dependent to the weights and the input of all these, in this case, 4 neurons. Not only this, but all of them. That's why there's always a summation involved here. So now assume your delta is available. You got it from the last layer. And you have this value coming from there. So now you're staying at, now you have the delta for the L plus 1 layer, L plus 1, and you want to come back to the rest, right? So now what we're going to do. Okay, so I put the whole high-level view of the network there just in case for your reference. So now you have to compute for the layer L. We expand the chain rule. And this value would be equal to that again, because the partial xil divided by partial sil is exactly the theta prime of that nonlinearity here, right? When we wanted to go forward for the forward pass, they would apply this to that, but when we have some error, we want to backprop, you have to get the prime of this with the inner function. But in order to calculate this, so as I mentioned, because each of these nodes are connected to all previous nodes. So suppose this is this node. So you had 3 nodes, for instance. So this relates to all those 4 behind. That's why you have to do a summation, because all those weights should be changed because of the error you have found here. That's why you have a summation of J1 up to D L plus 1, and you have to add this value multiplied by this chain rule. Okay, this would be equal to the sum of J from 1 up to D LH. The delta J multiply its W's, right? So we're almost done. Okay, so now we just need to compute this value for the rest. Okay, so again, you have the scheme there. So expanding this, you would have from the previous slide, you would have the sum of all those j's from I up to D LH of their delta LH. Oh, let me check if it. Yeah. Okay. And then again, you have to, coming back, you have to multiply them to theta prime of Si when we calculated here. So now this is the change we expect here from here to here. And here itself is the change we need to be done. So this is 1 and this is 2. Okay? Thus presenting in a vector space, so you would have the vector of delta L, all those delta inside. So compute that. You would have this, the vector of W, LH, all those hidden layers in the middle, and their delta LH. This funny thing here, and delta prime SL. And this is actually a pointwise multiplication. So when you have two matrices or vectors, this would be equal to, like you had this, these are the elements. If you had a pointwise multiplication, so it means that you multiply this to its pair, and that would be an output, right? It would be this, multiply that. Suppose you had square here, so you would have to multiply this to that, so square. So that's why we have a pointwise. In the vector space, we have to calculate it this way. And we know that this is always 1 minus theta square of SL. Let me just clean this up. And also for definition of W, you know that in vector space, you would have such a vector. And the vector representation of W theta prime SL would be this. They are in DL dimensional space in R. Okay, so now you're done. You just have to formalize it in certain steps how exactly the backprop algorithm works. And that would be your last slide for today. Okay, so if you want to recap what we learned today, and the slides. So these are our inputs, x and y, and the omega was the parameters, the weight parameters, and the output was a delta we got as the result of our classification. So partial E divided by the L of the last layer, L capital, right? And we have to, backprop towards all the layers L1 up to L capital L, right? So first, we have to run a forward pass to compute this to start, right? To begin with. So we have we can compute the example error or E of omega from the differences between the true value and the one we estimated. Second, the delta L for the last layer is the gradient of XL, the capital L. So this is the last layer. And that's that actually here. So this is for last layer divided by, pointwise multiplied by the theta prime of SL, right? And then we have to backprop these towards other layers. That's why we enter a loop here for L from L minus 1 for L minus 1 to 1, so the penultimate layer, because we already computed the last layer here. To the first layer, we do this. The delta L, the vector of delta L would be equal to theta prime SL pointwise to the weights of that layer connected to that layer, which was the summation of all of those neurons behind a specific node, multiply by the delta L plus 1, right? And then you would have to compute this partial E divided by L XL multiply delta L. So this is in vector space, so that would be the prime. And you have to do it in a for loop, and the error you got from your classification would be backprop, and you would adjust all your W's through your network to reach your first layer. And that would be only one iteration in neural network if you want to train it. And you had to train it for many times using SGD, and finally you would go down the optimization space towards your minimum, local minima, right? Do you still like neural networks after this? So have fun implementing your own backward pass. The other point is, yeah, we're almost done. The other point is, I guess you're going to receive a notification from the head TA about the assignments. Some of you wanted to do it individually. It's possible, but you're going to put yourself in a disadvantage because there's not going to be an extra point for doing it individually. So it's better you pair up and do it together. So chances are that you get more points. But it's up to you anyways. Okay, any questions? All right. So see you on Wednesday then. Have a good day, guys.